A very good afternoon I wish to my panels, Dr. Rose, Dr. Chang and Dr. JARIAH. I am VASEETHA Ravichandran from 4 BMFG Section 3 Group 1. Would like to present my final year project entitled The Influence of Hydrothermal Aging on the Fatigue Behavior of a Wood Polymer Composite. My supervisor is PM Dr. ZALEHA binti MUSTAFA. So without further ado, let's get started. WPC are more environmentally friendly and require less maintenance than any other alternatives for WPC. That is because WPC is classified under green material and it is less expensive, stiffer and stronger when compared with polymers. However, the fast advancement in industries have affected the development in the research on WPC where the resulting properties of the materials from lightness and improved mechanical properties to more prominent maintainability has implied a developing number of applications in areas such as building, construction, and automotive designing. Generally, WPC alludes to any composites that comprises of the mixture of any plant, including wood and non-wood fibers, and thermosets or thermoplastics such as polypropylene, polyethylene, and polyvinyl chloride, which are the four most common utilized thermoplastics for WPCs. Over the past decade, in the course of current global challenges with respect to carbon dioxide emission and climate change, the concept of green environment has become more mainstream. Therefore, the reapplication of wood-based products as a renewable resource used in construction and automotive is highly contemporary. Currently, WPC are well established and the market is ripe for non-structural application, but recently researchers have been working to expand the use of WPC in structural applications. Although the research and development in WPC is growing rapidly, but these materials still require specific considerations before being adopted by industry in structural applications. Firstly, since the material's deformation mechanism under short-term and long-term mechanical loading is not always the same, and only the tensile test is not sufficient to do a prediction of their long-term load-bearing application, thus for safe fatigue design, the study of fatigue behavior of the composites is very important, particularly if the rubber-wood polymer composites are subjected to use in long-term load-bearing applications. Next, since the mechanical properties of WPC changes rapidly in human environment, the study of hydrothermal aging is also crucial in determining the durability of WPC. For example, the difference in damp heat sensitivity between pores, fibers, and resin matrix cause swelling in the matrix and fiber, which generates internal stress and the growth of microcracks along the interface, leading to dimensional instability and mechanical property degradation of the composites. Therefore, it is essential to examine the hygroscopic properties of rubber-wood polymer composites in a hydrothermal environment and understand their performance changes both in static and fatigue conditions. Moving on to the scope, this study focuses on the influence of hydrothermal aging on the fatigue behavior of natural composite materials. The materials consist of rubber wood fiber reinforced with recycled polypropylene. Water aging duration will be up to 90 days at room temperature. Fatigue testing will be conducted in force control at 4 Hz till failure. Mechanical properties will be observed on strength, rigidity, and energy absorption due to hydrothermal effect. Meanwhile, the objectives of this project are: first, to evaluate the static properties of WPC after water aging; second, to compare the fatigue life of the non-aging and the aged WPC; and lastly, to evaluate the effect of water aging on fatigue properties of WPC. Next up is the literature review. Throughout the writing of Chapter 2, I have reviewed more than 30 journals and classified all the important points to support my research as shown in this slide. In the next two slides, I have summarized the most crucial observations to support the problem statement, scope, and objectives of my research. Firstly, Moreno and Sarin on 2017 stated that WPCs can be produced from environmentally friendly materials such as wood fibers, unused natural resources, and recycled thermoplastic resins. Meanwhile, Wei Wang on 2020 stated that the tensile and fractural strength of wood powder reinforced polypropylene composites with soaked dampness content basically depended on the polypropylene matrix, and wood powder had small strength impact on the matrix. Next, M. Polinan on 2013 mentioned that consolidating new additives and coupling agents such as reused polypropylene within the wood thermoplastic matrix driven to way better grip between the polar hydrophilic wood fiber and the non-polar hydrophobic thermoplastic components, and subsequently improved the mechanical properties of WPC. Besides that, in an experiment conducted by China Rum Srivabut on 2017 with WPC sample using rubber wood fiber as function of contents of nanoclay, talcum and calcium carbonate as fillers, showed that the calcium carbonate at 7 weight ratio percentage of composite had highest mechanical properties, and the water absorption and thickness swelling of composite samples decreased by adding chemical fillers, which is calcium carbonate. Moving on to the next, Michael P. Walcott on 2010 said that it appears that the coupled wood flower PP composites perform superior and show higher reliability index than their counterpart uncoupled pairs due to improved interfacial holding between wood flower reinforcement and matrix polymer within the coupled composites. In addition, Sylvia Bethany on 2011 proved that the compatibilized 30% coir fiber reinforced PP composites displayed longer fatigue lifetimes compared to pure PP or non-compatibilized composite. Followed by that, on 2019, she also stated that the feasibility of pulverization of wood flour on the fatigue performances of polypropylene/wood flour composites depended on the initial wood flour particle characters. Next, Vauthier on 2010 mentioned that the hydrothermal defects made in the bulk composite during the water sorption step initiated a critical decrease in fatigue properties, particularly after aging in immersion. These overall losses of properties were linked to the drop in the measurable dispersion of the fiber strength after aging. Lastly, in an experiment carried out by Li and Zhu on 2015 showed that after 17 weeks of immersion of WPC at 60 degrees Celsius, their results appear a diminish in the tensile strength of roughly 15% for the water-saturated material and of around 37.5% for the aged and the dried example. Now, moving on to the materials. The materials used in this study is the wood polymer composite WPC in the form of granule containing recycled polypropylene about 50.3%, rubber wood flour about 44.5%, MAPP about 3.9%, UV filler about 0.2%, and lubricant about 1% by weight ratio. Calcium carbonate was also added into WPC sample at the ratio of 7% by weight to improve their mechanical and physical properties. The granule was optimized and extruded by the University of Prince Songkhla, Thailand, and is used as supplied. Next up is the methodology. The process flow of the research methodology used in this study is as shown as below. First, sample preparation. Several sets of tough-wood specimens will be prepared, where 8.22 gram of WPC granules will be compressed at 190 degrees Celsius. Constant pressure of 2 tons is given for 10 minutes, 7 tons for 15 minutes, and cooling for 10 minutes. Then, hydrothermal testing. 5 specimens will be used for hydrothermal testing, referred as aged, for up to 90 days in distilled water, while another 5 specimens act as control and referred as non-aged. Next, quasi-static tensile testing. Both aged and non-aged specimens will be tested with 20 kN load cell and crosshead speed of 2 mm per minute. After that, fatigue testing. The specimens will be tested under fatigue tester machine at 4 Hz and R equals to 0.1 and at levels corresponding to 40, 60, 70 and 80% of the ultimate tensile strength until fracture. The round-out is considered after 1.5 million life cycles. And finally, morphology analysis. where SEM will be used to observe the surface structure of the specimens. Next, I'm going to explain my work planning. In the next semester, I will modify the drawing dimensions shown in this slide, which I've done during my third year. Then prepare mold for specimens using CNC machining, prepare dog bone specimens using manual hot press, and carry out experiments during semester break because I might need approximately 4 months to complete my research. So this slide shows the Gantt chart. Here is the distribution of my work planning throughout my semester. Since I wish to start early, so I am including my semester break too, and this will be my work planning for the upcoming days. Last but not least, the problems and solutions. The problems that I might face throughout the completion of my final year project are first, time consumption and availability of equipment. And the only solution is to start early during semester break because when I start early, I can finish up my experiments early and spend more time on the discussion analysis. Moreover, I don't have to wait for my turns to use the equipment in FKP next semester. In that way, I can save time and reduce last minute stress. We have reached at the end of the slide. That is all from me and thank you so much for the time.